Good afternoon to everyone who has joined. There's still people coming into the session, so we're just giving it a 30 seconds or so to let everyone in. But I'll actually start with the introductions, I suppose, for today. Just to thank everyone for coming to the session. Looking forward to a good talk this lunchtime. And we have Aidan Edwards and John Davison and Shane O'Regan with us today. So I'm actually going to hand straight over to Aidan. We are a little bit tight for time with today's presentation. I guess the John will explain this, but we initially had it as two different sessions and we had to kind of combine it into one. So with that in mind, it's kind of overview level, fairly speedy. And there's maybe an option the lads have kindly said they if there's a particular topic that people are interested in for a more in-depth view, we could maybe look at arranging that at a later date. So not taking up any more of your time, I'll hand you to Aidan. Thank you.
Good afternoon, everybody, and thank you for joining. I'm Aidan Edwards. I'm the Area Sales Manager in Ireland for Measurement Products. I support Collie Automation. I'd like to thank Sheila, firstly, and Sinead for setting this up for us. And also, I'd like to thank Collie Automation for their involvement in this with Engineers Ireland. So without further ado, I'm going to introduce you to our product manager for pressure and temperature, John Davison, and look forward to this session. So enjoy, people, please, and thank you very much. John, over to yourself, sir.
Okay, cheers, Aidan. So hang on, it's not stepping through. Just give me a moment. Technical issues. It's always a good. There we go. So it's starting to step through now. So I'm the product manager for pressure, temperature, and level for ABB. So I cover the UK and Ireland. Just a quick introduction to myself. So I've spent 37 years in instrumentation. I know I don't look that old, but that's how long I've been involved in it since a young lad, covering things like oil rigs, chemical plants, high-tech industry, research facilities. I've been at ABB around about 10 years, 8 years of which I spent specifically in the water industry. I work over in Ireland with Aidan and plus the team at Cully's. So they are representatives in Ireland specifically covering the water industry. And I love a measurement challenge. So please, at the end, if you get questions, throw them through, or we can look to arrange a separate session separately. As I think it was Sheila said earlier, it is a bit of a whistle-stop tour. Each of these topics I would typically spend an hour or more on. So it is very much a whiz through. Brief overview of what we're going to cover: what and why, pressure and temperature, basic theory, challenges, solutions on both topics, and also a little bit at the end on some disruptive technology and temperature and the digital world from the point of view of instrumentation as well. So a very brief overview of ABB. We're a big multinational. We cover products like electrification, things like drives and motors. We manufacture robots. We have a process automation division. So Aidan and I sit in that division, which is, we also sponsor Formula E. The process automation division is where the instrumentation products sit. So we manufacture a whole range of field and flow instrumentation, analyzers, flow meters, pressure, temperature, level equipment. Analytic equipment for both liquid and gas, force measurement equipment, and we manufacture around the world. I'm not aware of any manufacture in Ireland, certainly for our part of the business, but we do manufacture in the UK, which is something we're very proud of in this day and age. So moving on to the topic in hand, what and why pressure and temperature measurement. So I guess the first question really is what is pressure? Well, pressure in very simple terms is force per unit area. So I'm old school. I think in pounds per square inch. Modern terminology is kilograms per centimetre squared, but effectively they mean the same thing. It's the amount of force applied per amount of area, unit area. Temperature is an interesting one because everybody thinks how hot or cold something is, but it's actually the kinetic energy, the particles, so how active the particles are in a product. And if something gets cold, they're less active. Something gets hot, they're more active, but we use that to then determine the temperature of a product. Why measure them? It's a simple question. Well, there's a great picture that was in our press of one of our local water companies who had a bit of an issue, which is obviously very embarrassing. But also from a serious point of view, if you don't measure something, you can't control something. So from the point of view of process safety, both pressure and temperature are quite critical. Also, if you want to optimize processes, really you need to start measuring, especially temperature, but also pressure. So as a good example of this, digesters. If you control your temperature, you can optimize the amount of biogas you produce from a digester. If you get it wrong, you don't produce as much biogas. If the temperature is too high, potentially you can kill off the bugs. So both products, pressure and temperature, are used universally across both the water and wastewater process. So this could be something as simple as temperature monitoring on a motor, through to pressure monitoring in tanks. So we talk about hydrostatic level, it's actually pressure monitoring, all the way through the process, really, all the way through to the end of the process where potentially you're doing final effluent. And again, temperature is sometimes used before it goes out into the water course. So basic theory, pressure. Pressure comes in effectively three versions: absolute pressure, gauge pressure, differential pressure. So absolute pressure is effectively the reference point for the measurement. So if you're out in space, there's no atmosphere. So your reference point for absolute pressure is a full vacuum. Gauge pressure, well, where it's at on this planet. Gauge pressure is then referenced the atmospheric conditions. Now, inconveniently, the atmospheric pressure changes. So gauge pressure devices are actually differential pressure instruments. But what you're doing is you have one connection onto the process to measure the process pressure, and you then effectively have a compensation port in the device as well. Sometimes it's not always obvious, some devices it is. Differential, very simple, it's a measurement between 2 points. So you can also use pressure. We're talking mainly about pressure here, but you can also use pressure to determine flow, such as the differential pressure example there, level, interface, or density. Interface and density are less commonly used in the water industry. As a matter of fact, I don't think I've ever seen one, if I'm honest, but certainly flow is used and level definitely used. Translating that into product, typically for a gauge or absolute pressure transmitter, you've got a single connection into the process. Differential pressure, you've got two legs, and you also have something called a multivariable pressure transmitter. That's effectively a DP transmitter, but also measures the absolute pressure, and you can put a temperature input into that as well. So hence the phrase multivariable. You're measuring absolute pressure, differential pressure, and the temperature. That's typically used on flow applications where you're measuring mass flow of gases, less commonly used in the water industry. Range of accessories. We'll be touching on some of these later, but effectively talking about manifolds for isolation, remote indication, because if your device is up in the air, sometimes you need to see it on the ground, and these wonderful things called flushing rings, which we'll touch on later. So, typical pressure applications. Hydrostatic level. So, if your tank is open to atmosphere, if it's a vented tank, you only need a single connection to the tank, so you can use a gauge pressure device. And effectively, all that's doing is measuring the weight of the fluid in the tank. If it's a closed vessel and there's some gas in the headspace of the vessel, then you would need to use a differential pressure device, because what you need to do is compensate for the pressure in the top of the tank, which is also then pushing down on the weight of fluid in the tank. So hydrostatic, two ways of doing it. You could use a differential pressure device to measure on an open vented tank. You just leave one leg open to atmosphere. Now, one key thing sometimes people do miss on hydrostatic level, if your fluid is not water, then SU1, you do need to compensate for the density of the fluid. So if it's a typical sludge, it will be a little bit heavier than water. So do compensate for the density. And normally you can do that within the device. If not, you can do it back at the PLC. You just need to apply a correction factor. Flow, historically was quite common in the water industry, probably less so now, but you will come across it sometimes on things like aeration lanes, ozonation, those kinds of applications. Effectively, that's a two-part measurement system. So you've got a flow element that sits in the line, and there's examples of some flow elements on the image there.
John,
and the pressure transfer.
excuse me, John, we're not seeing the presentation, we're just seeing yourself. So,
Oh, really?
Yes.
Okay, that's odd.
No, John, I can see the presentation on you.
Oh, can you? I'm only seeing John.
Yeah.
Sorry, my apologies. Okay, no problem. No problem.
Okay. Well, I guess if anyone else has a problem, ping something in chat. But if everyone else can see it, happy days.
No, they can see it in the chat there. I can see.
Yeah. Okay. Brilliant.
Yeah.
No, good.
Apologies.
So that's all right. And it's worth shouting in. So flow, less common now. Two parts to it. You've got the flow element, which sits in the line. Your pressure transmitter sits on the top, and your pressure transmitter takes differential pressure created across the flow element and calculates a flow rate. Now, that isn't a linear relationship. So this is where you get things called square extraction, because you get this non-linear relationship. You can do that in the pressure transmitter. Pressure transmitters these days are very clever. So you just set the device up to say, okay, I'm measuring differential pressure, but I'm actually want to give you a flow output. One thing you need to remember to do is only do that in one place. So don't do it at the pressure transmitter and don't do it at the PLC end as well. Density interface, I'm going to skip over. As I say, I've very, very rarely come across that in the water industry, but effectively, you're talking about a differential pressure device and it needs both legs wetted. So golden rules, devil's in the detail. So what are you measuring? Gauge pressure, level, flow, the working range, the overpressure, fluid properties. All these kind of parameters is what us as ABB or other suppliers will come and ask you lots of annoying questions, because really we need to define exactly what you're doing. Do you just want a gauge pressure device? What's your process connection? Is it going in a hazardous area? That's a very simple one. But once you get into things like level, we might ask a few more questions. It's also worth letting us know issues like if it's a condensing fluid, if it's a fluid that solidifies, if it's abrasive, it's corrosive. Again, we will tend to recognize a lot of the applications, but sometimes your own operational experience is very useful as well. Process temperature, location, and environment. So you consider the right mounting point. So if it's going on a gas service, especially if it's a gas like a biogas, but there's potential of condensation, just consider where you're going to mount the instrument. Because if you've got the instrument mounted as the example on the right here, and that condenses in that leg, you will get measurement errors. So what you need to try and do on something like a biogas, where potentially it'll condense, is to allow any condensation to run back into the pipeline. So again, these kind of things are covered in the manual, but I never read the manual. I don't think most people do. So just really think about where you're mounting the device and is it going to create problems. If you're remote mounting the transmitter, so it's not mounted directly on the line, typically people have used something called an impulse line, which is just a piece of pipe going from your pipe work to the device. Just consider, again, the impact of using impulse lines. So is it condensing fluid? If it's water that's going down there and it's sat outside, will it freeze, for example? Also, if it's a product that can solidify, such as a waste product, again, just consider the implications if you're using impulse lines. This is where the example on the right can be quite useful. So what we're doing here is effectively taking the impulse lines away and fitting a diaphragm seal to the assembly. And that diaphragm seal is then sealed at the process flange end or the process tank end. And the capillary you can see there coiled up acts as your impulse line. And that can resolve some issues sometimes you see on some applications. Isolation. This is a classic one. So the example on the left there, nice little pressure transmitter mounted on a tank, measuring the pressure in the top of the tank. But to take that device off, if you need to calibrate it or if you need to replace it, you would have to shut that whole tank down. And if it's something that's horrible in that tank, you'd have to basically empty the tank, clean it, vent it, etc., just to take a simple pressure transmitter off. So this is really think about the installation again. So how am I going to calibrate the device? What isolation do I need to use? And this is where things like manifolds can be quite useful. So the picture in the middle there shows a manifold. Also, the example on the right there is sat on a digester tank, measuring the level in the tank. And in that case, they've obviously got a great big valve they can shut off just so you can isolate this device. And quite often that's just for a routine check of the device. It doesn't necessarily mean there's a failure. But again, you don't want to have to drain a whole digester just to take a pressure transmitter off. So, challenges and solutions. What the typical challenges we see in the water industry? Abrasion. So things like boreholes, you can pull sand out. You can pull grits. I appreciate there's supposed to be degritting processes in the water industry, but again, sometimes grit gets pulled through the system, especially on older sites where the degritting doesn't work very well. So abrasion can be an issue where you've got particularly aggressive or abrasive particles in there, sand, grit, things like that. Blockages. Unfortunately, the way the world, the waste industry, by the nature of the product, the stuff can solidify. You can get ragging issues, things like that in there. So blockages can be a challenge. Temperature, but this is also from the point of view of, does it get very cold? Can it freeze? Which we touched on earlier, but also you can sometimes you will come across boiler applications. Sometimes, especially where you've got CHP or THP producing biogas. And the last thing really is just your pressure range. So they're kind of your key challenges and solutions we'll be looking at. So abrasion, typically where? Well, we've touched on that already. Anywhere where you can get an abrasive particle come through. The easiest way of mitigating issues with abrasion is just consider your mounting. So just try and mount your device so it's not going to wear effectively. Now, there's lots of ways in doing that. A recessed diaphragm or a flush diaphragm is a simple way of doing it. Where you do have known issues with abrasion, you can get very hard coatings on the diaphragm of the pressure transmitter. An example of there, the picture there on the right-hand side shows an example of what's called the Diaflex coating on a typical pressure transmitter. So Diaflex is basically it's a PVD coating, physical vapor deposition coating. It's designed to be a very, very hard coating, and it's very similar to the sort of coating you would put on tools to make your drill bits last longer, that kind of thing. But it really does extend the life of the device. Other coatings are available. That's an ABB solution, but whoever you select, if you do see abrasion problems, just think about this kind of solution, really to extend the life of your device. So that's abrasion touched on. Blockages, well, where? Well, that's an image of a digester with some of the pressure instruments highlighted. Effectively, anywhere on the waste side, you can get problems with blockages. So some examples there: slud digesters, actually filters. So we get RGF or GAC filters on the clean water side. You can have problems as well. So sometimes you get filter media carryover into impulse lines, so that can cause problems with the device as well. Not so much blocking, but it causes measurement problems with the device. Lines freezing. There's an example of you blocking a line. Simple solution, use a flush diaphragm. So there was an example of that in the previous and in the next slide. Or use a diaphragm seal, really to minimize risks. Isolation for the process, we touched on earlier, really is essential for checking and cleaning. And if you do have a flange design, this is where flushing rings really come into their own. So mount a flushing ring so you can do in situ flushing and also in situ calibration checks without having to take the instrument off. Remote diaphragm seals include a fluid-filled capillary, which will also extend the temperature capability if needed. So again, this is quite useful in applications where potentially you can get freezing. So picture on the left-hand side is a standard pressure transmitter design. The diaphragm tends to be up inside the threaded area there. You can see that's going to block quite easily. And again, the image at the bottom shows a typical differential pressure design. Again, you can imagine if you connect sludge into that, it's going to block quite easily. So what we tend to do on waste applications is move to a design more like this, what we call front bonded diaphragm. Well, where rather than the diaphragm being sat up inside the body of the instrument, it's sat right flush at the end. Or you go for a flange design, and again, the diaphragm is sat effectively at the end. Sometimes diaphragm seal design is useful. We touched on earlier if you need to remote your device away from the process because it's convenient. or because of just accessibility. But this is where you can also mount what's called an extended diaphragm on there. So if you've got a standoff point, which could potentially block, if you extend your diaphragm in, it just keeps that flush inside the vessel or the line. And the last thing is really just a flushing ring example. The flushing ring is the disc. That's typically 1 or 2 hole disc, stainless steel disc, or other materials available. And that's really just designed so when it's installed, your flushing ring is sandwiched in between your process flange and the instrument flange. You can isolate it from the process. You can use the holes to flush it through with water or air. Once you've flushed it through and cleaned it, you can then, if you want, come along with a calibrator and calibrate it in situ. Okay. Diaphragm seals, we've talked about a lot. There's a whole range of diaphragm seals. I could talk to you for more than an hour just about diaphragm seals. Typical examples of diaphragm seals we would use in the water industry are some of the examples here. So flanged with a fixed flange or a rotating flange, sometimes with an extended diaphragm, depending on the application. But also that little seal at the bottom there is a design where I've talked about front bonded, effectively the diaphragms at the end, but it's a threaded design, so you don't have to go for a flange, which again is sometimes very useful on process lines. Key thing with diaphragm seals is you can buy them with a device, or you can buy them and fit them separately. We always recommend supplying them with the device, purely because where we assemble this as a complete assembly, it comes already attached and tested to the instrument. We fill them under vacuum conditions, so we make sure there's no air in there. A capillary seal system is effectively a hydraulic system. So the process is at the right-hand side of the image, pushing it on the diaphragm, and you rely on hydraulics to transfer. That's the instrument sensor. What you don't want is air in there because it causes measurement issues. So this is why we recommend it comes as a single assembly. So that's touched on blockages. If we move on to temperature, really temperature, there's 2 challenges, if you like. Is it hot, which you'll typically see on CHP or THP engines generating the biogas, where you've got things like the boilers. So your boiler can run at 200 degrees plus. So is it hot? That kind of temperature is normally outside the range of a standard pressure transmitter. Or does it get very, very cold? Can you have problems with freezing if it's outside? You can mitigate a lot of the problems on high temperature applications just by mounting the device carefully. So example on that we got on the left here is sat on a boiler. And all the boiler is obviously quite hot. I think this one was running about 240, 250. That device sat on the top there is only rated to 120 degrees. But what we have is this extension piece here. And this has actually got the little pigtail siphon on there. What you effectively have is the top leg here has got water in it, got condensate in there. So the hot steam from the boiler comes up, pushes on the water. So you get a hydraulic system here, but you're stopping the hot steam actually reaching the instrument. As a rule of thumb, we recommend a meter to drop about 100 degrees. So where we've got these on things like process tanks, generally the approach is just a separation. What you do need to consider is what the impact on the process would be if you do separate it. So, for example, if it's a liquid and you cool it, is it going to solidify? If it's a gas and you cool it, is it going to condense? And again, you then back into just consider the mounting requirements. The other option we can look at, if it's high temperature, or actually if it's low temperature, is move to a diaphragm seal system. So the standard device, as I say, is rated to about 120 degrees C process temperature. But by using a diaphragm seal system, what you're effectively is removing it away from the hot stuff, and it really extends the capability of the device. So by moving to a diaphragm seal system, you can get designs up to around about 400 degrees process temperature, depending on the fill fluid you pick, etc. But it does really, really help where you do have to have the device direct mounted and you don't want separation. The example we've got there in brackets, it mentions flushing rings. So there's an example of an install with a flushing ring, which if you've got good eyesight, you can probably just see here sandwiched in between the instrument flange and the process flange. And that's just what a flushing ring is. It's just a disc sat in there, and there's the plug at the top. There'll be one at the bottom, so you can just remove, flush it through. So, pressure challenges, pressure range. The key thing here really is just look at what you are measuring from a range point of view and select the right device from that. So I've given an example based on 2 ABB products. We manufacture a product, sort of mid-range product called a PGS 100. That has a whole range of sensors in there depending on your measurement range. But if we pick, let's say, a 400 millibar sensor in that product, its maximum overpressure rating will be 10 bar. If we went into the next product lineup, what ABB call the 266 HSH, exactly the same sensor range, 400 millibar sensor, but that device is capable of a much higher overpressure range, 140 bar, and it will recover from that. That's the key thing. So you can overpressure that device, bring it back down to 400 millibar, and it will still work. So just again, think about the whole requirements of the application. So if you've got these mounted on things like pumps, especially pressure boosters, they can generate quite a high pressure spike. What you don't want to do is continue to break your pressure sensors because you're going past your overpressure range. So do look at the whole specs of the device. Also, sometimes if you're measuring very low pressures, if you look at the very low end of the range, sometimes it's worth moving to, rather than just a gauge pressure instrument, sometimes look at differential pressure instrument, because sometimes that gives you a much lower range capability. So again, just look at the specs very carefully. Really, I'd encourage you to discuss this with the supplier because we are the experts in our own products. And as long as you give us the necessary information, we'll look at what solution fits you best. So that's very much a whistle-stop tour of the pressure side of things, if you like, some of the challenges and solutions that are available. What I'm going to do now is do the same thing on the temperature side. The pressure is probably the biggest part of it. There's a little bit on temperature as well, so maybe 20 minutes. So we should have a little bit of time at the end for a Q&A session. So temperature measurement, type of devices. We've got purely mechanical devices, so the old liquid-filled thermometer you may remember from your childhood. I do, with the doctor sticks in your mouth to measure your temperature. Because these things now are electronic. You can get bimetallic systems here. So as you change the temperature here, it flexes this assembly here and picks it up on a pointer scale, which you can also have a rotary transmitter connected to. Probably more common for process measurement are a thermocouple. So this you might be used to at home for your heating. So that typically have a very simple bimetallic strip in there, which is effectively a very basic thermocouple. But also something called a resistance thermometer or RTD. Most common unit I come across is Celsius, so degrees C. But if you're in scientific communities, you'll see Kelvin. Where I deal with our American colleagues, they always talk about Fahrenheit, so instantly I've got to then convert that to degrees C. But the most common we see is degrees C. So the most common measurement type device for a process measurement in water and wastewater is likely to be an RTD. And that's commonly what we supply, less likely to be thermocouple. The main reason is thermocouples don't tend to be as accurate. An RTD covers the kind of range you're going to work across in the water industry without any problems. And actually an RTD is far more accurate than a thermocouple. So what is an RTD? A resistance temperature detector, RTD. Effectively, it's an element that as you change the temperature, it changes resistance. Now you can get thin film designs. So this is where you basically spray something on a substrate. That's one design we can supply, but you can also get wire wound designs. Each has their own benefits. The thin film design tends to be a little bit cheaper, but doesn't tend to be quite as robust. Now, when I make that comment about robustness, a thin film design will quite happily sustain 10G, which most people don't. But if you get much higher sort of vibration levels, this is where sometimes a wire wound comes into its own. Also, a wire wound design will cover a much wider temperature range. So wire wound will do minus 200 up to around about plus 800, whereas a thin film is around about 400, 450 is a maximum. But again, that's perfectly fine for, I think, all applications in the water industry. Relationship wise, it's not quite a straight line. So you'll see these as PT 100. What that means is at 0 degrees C, that's 100 ohms. And you can check a PT 100 very, very easily. So you can go and actually measure the resistance that the device is giving you, and you can check it's correct because you know it's 20 degrees today, you know what the relationship should be, and you can just pick it up on the lookup table. So the most common type of RTD is PT 100. There are other types available. PT 1000 is one sometimes that's used, typically because that gives you historically a much better resolution. And that tends to be used scientifically. So sometimes some of our analytical kit uses a PT 1000, but actually with modern electronics, PT 100 performs probably just as well. So we've talked about PT 100. Very basic sensor is a two-wire design. So there's your hot element, if you like, which is the red part here. Actually, more commonly, you'll go for a 3 or 4 wire design. The reason being, as soon as you connect wires to a 2-wire design, you've changed the resistance of the design. By going to a 3-wire design, by connecting wires to these, you can then compensate for what's called the lead resistance. 3-wire, again, is probably the most common. Unless you've got a particularly long cable run between where your sensor is and where your transmitter is, then people would typically go for a 4-wire. I tend to specify them as a 4-wire design, purely because 3-wire and 4-wire cost the same. But you can connect a 4-wire design as a 3-wire, but obviously if you've got a 3-wire, you can't connect it as a 4-wire. So I tend to suggest people go for 4-wire. Duplex sensor. So you might come across something called a duplex sensor. That's effectively 2 of these all within the one element. So you've got 2 sensors within the one device. So that's your basic element. What you then do is package those into what's called an MI cable, mineral insulated cable, because the basic sensor is not suitable to be put into your process. And actually not suitable to be left out in the open environment as well, because it will affect the sensor element. So you package them up effectively to protect them into an MI cable. That looks like solid rod, and actually when they're quite short, it is solid. But when you get very long runs, so I've seen runs 11 meters longer, they coil up. So it is effectively like a cable. The key thing is your measurement is at the very, very end of that. So that sensor we talked about, your PT 100 sensor, is sat very, very much right at the end of that element. So that's your measuring point. So we've talked about how we package these things up. Okay, that's great, but how do I now turn that into an instrument? Well, typically they come in 3 forms: a surface mount design, where it's literally just clamped on the outside of the pipe. So the clamping arrangement, your sensor will be sat here. And this is your connection off to the process. So you might have a transmitter or something sat in the head there. An intrinsic design with a thermal well. So what you're then doing is putting your temperature sensor, your RTD, within a thermal well. A thermal well is purely there to protect that element, because you're then going to put this into water or sludge or a boiler or a chemical that's potentially quite corrosive. That thermal well, its only job is to protect that sensor. And probably the most common design you see within the industry is the thermal well design. So it's inserted into a thermal well. Also, more recently, non-invasive designs have started to come to the fore as well. So the advantage of a non-invasive design is it works just as well as a thermal well design, but you don't need a hole in the pipe. All these 3 solutions provide point temperature measurement. So if you want to measure a number of points in a digester, you need a number of instruments. Saying that, you can get something called a multi-point temperature sensor. So that wonderful kind of Christmas tree arrangement, if you want, there is there a number of devices all mounted on a single flange. So they're effectively individual instruments, but there's only maybe one mounting point in the process. So they're all connected into the one flange. You can also have a multi-point design like the example on the right-hand side there. That multi-point design is effectively a number of elements, but all within a single tube. They're really useful where you've got a tank where you've only got a single access point. And I think the longest one of these I've ever supplied was about 23 feet long, with about 11 measurement points in there. Really useful if you need to measure a number of points in a tank and you've got limited access. Cable temperature sensors, typically used for surface mounting. Sometimes you'll see these kind of designs mounted on motors and such like as well. One of the disadvantage of something like a cable type sensor is basically the accuracy. They're very good for giving you a rough indication, but not the most accurate design. So installation practice. Again, this is where the devil's in the detail, if you like. So required immersion length. So this is where we're talking about on a process line. So if you're mounting this on a, let's say, a 6-inch line, we recommend around about a 1/3 to 2/3 insertion in the line. Most people go for 1/3 because it's much easier than 2/3 insertion in the line. That's the general rule of thumb that's used. So for a 6-inch line, you need at least 2 inches in the pipe. But do consider your nozzle standoff as well. So if your nozzle height is 4 inches and you want 2 inches in the pipe, that's a 6-inch length, 150 mil length thermal well. So do consider that. And we sometimes see people caught out like that as well. What you don't want is you don't want your temperature measurement set up inside the nozzle, because then it just won't work accurately. Mounting on the pipe, if you've got a very small pipe or you have other mounting constraints, you can look to mount them on things like elbows, which can help if you've got a particularly small line. So you mount them at a 45-degree angle, or you mount them on an elbow. That can also help where you've got specific application problems, some of which we'll touch on a little bit later. So if you've got a product that's liable to block, if you put it at a 45-degree angle, that can help. So key considerations: define your requirements. We've kind of touched on that already. How long? How long is the piece of string? Again, we quite often get inquiries for temperature devices where people say, I want a temperature device to measure 0 to 100. You're like, right, okay, but how are you connecting to the process? What's the line size? What are you doing with it? Try and give us as much detail as you can, I guess. Mounting, we've touched on. Do you want surface mounting? Do you want it in a thermal well? Can you go for a non-invasive design? The last thing is wake frequency. And the flag's a good example of this, because if you imagine that flagpole there, that flagpole is your thermal well, and as the breeze goes past that, your flag flaps in the breeze. So on some applications, you will have to consider wake frequency. So there's a good example of what can happen. You get these eddies as the fluid passes down the pipe. And these eddies, as your fluid goes down the pipe, can create, as it flows down the pipe, the fluid, it will try and push that thermal well forward, but also these eddies that will come off will try and swing it side to side. So what you may need to do is you may need to do wake frequency calculation. Now, there's two standards for this. There's a DIN standard, there's an ASME standard. ABB don't have to do it, but we can do it for you if you want. Other suppliers can do it as well. But certainly if you're on things like boiler applications, anything with a high velocity, do sometimes think about your wake frequency calculation. On your standard sludge applications, it's at 0.5 meter a second velocity down the pipe. I wouldn't worry about it. It's never going to be an issue unless you've got a particularly long thermal well for some bizarre reason. But certainly anything with above 1 meter a second, certainly above 2, if you're on the sludge side, do think about wake frequency. It's important because effectively you can shear off that thermal well, and they tend to go at the mounting point. So at where it's connected into the process, be that a thread or a flange, they tend to shear off. Now, okay, if it's the brown stuff that's in the pipe, that brown stuff now has a pathway up into your electronics and into the outside world, which isn't ideal. But if that's a steam line, obviously you can see the implications are potentially far more serious. So I would say do always have a little think about it. If you're not sure, ask your supplier. Do I need to think about wake frequency? And we will have a feel for whether it needs to be done. And actually, we can do a draft calculation just to check if we feel it may be an issue. And what you'll get is basically a pass or fail. If it fails, we'll really look at the design of the thermal well, and that might be go for something a bit shorter, go for something a bit thicker, maybe look at one of the other solutions that's available if we can't get it to pass. And I know from my own experience, some applications where you need to cover a normal operating condition, but actually a failed design condition, it passes fine under normal operating conditions, but under the theoretical design fail conditions, this is the process. If something fails in the process, we could see these conditions. Sometimes the wake frequency will fail into those conditions. So effectively, you then need to go re-engineer your thermal well. So typical applications, there's a whole swathe of these in the water industry, from oil monitoring and gearboxes, motors, those kind of things. If your motor runs hot, you need to know before the thing catches on fire. Digesters and tanks, so side mounted in digesters, top mounted in digesters. The longest one I've supplied on a digester was 11 meters. Just bear in mind, if you're mounting it on the top of the digester and your thermal well is 11 meters long, you then need to lift it at least 22 meters in the air. So you need a very big crane. Wells and chambers. So sometimes you monitor the conditions in a well or a chamber just to make sure you're not under septic conditions in there. The one thing I would say about if you're going to mount it in a well or a chamber, this design here, thermal is all stainless steel, but this was also supplied with the stainless steel housing, whereas if you look at the design on the left, that's an aluminium, purely because that environment in there is quite aggressive. So if you put a standard housing on there, potentially that will corrode and within probably a year or two, decay and die. So again, just think sometimes about, do I need to go for a stainless housing? Yes, it costs me a little bit more, but it means I'm not going to replace my instrument every couple of years. Process monitoring on pipelines, very, very standard. Be it, sort of sludge, be it water, be it steam, even actually aeration lines, thinking about it, sometimes they go on aeration lines. What you don't want is the air to get too cold in an aeration line, because potentially you get fluid condensing out, and that affects the efficiency of your aeration. So key challenges, very similar to the pressure transmitters in a way. So abrasion and corrosion, not so commonly seen, abrasion and corrosion, but if you are measuring in perhaps one of your dosing tanks, something like that, so if it's a caustic tank or something similar, do let us know, because you might find stainless steel only lasts a couple of years, and maybe we need to go for a Hastelloy or something similar, or a coated design. Abrasion tends to be less of an issue. I know some sites have a problem, but that tends to be a problem over quite a long time. And again, you can mitigate it through some of the mounting practices we've discussed. Wake frequency, we touched on that already, and the importance, because you don't want this thing to crack. Product buildup and ragging is probably the biggest issue. You will see, certainly on the waste side, where because you've got a thermal well design stuck into the process, you can get buildup. You're going to have to remove them. You're going to have to clean them. And if you've got a thermal well system, historically there was no real solution to that other than just maintenance. But although this is where now, with the introduction of new technologies, new non-invasive technologies, you now have an alternative. So this is what ABB call the NIMVA. This is the non-invasive system. So a traditional thermal well is inserted in the pipe. The non-invasive clamps on the outside of the pipe. So there's no shutdown required. You can mount it on a process live. There's no holes in the pipe, so obviously that gives you a major safety issue. And there's no engineering consideration, so you don't need to think about your nozzle. You don't need to think about wake frequency calculation. So how does the thing work? Well, conventional invasive thermal well, you put your sensor into the thermal well, your sheath if you like, and it measures at that point in the process. The non-invasive, we're effectively using the pipe as the thermal well, is the best way of describing it. So unlike a conventional surface mount system, which only has a single sensor, we actually use two sensors for our non-invasive design. So you've got one touches the pipe wall, and it has to touch the pipe wall, not the insulation. It has to be in contact with the pipe wall. And the second sensor is a reference sensor, purely to correct for the changes that happen within the ambient conditions, the environment on the pipe. Setup wise is very, very simple. So to set up a non-invasive device from ABB, you literally just put your measurement range in. But what we do is we do a lot of, I say a lot, we do a minimum amount of pre-qualification, if you like, which is we talk about, okay, what's your pipe schedule? What's your pipe size? What's going through the pipe? These basic conditions that we would ask probably anyway for a thermal well design. So we ask very, very similar questions. And what we'll do is we'll run it through what's called a performance predictor, just to make sure the device is suitable. Because it's not suitable for all applications and non-invasive, but it's suitable for a lot of common applications. Sort of range you can use it for, line size range, actually smaller than DN25 now, we can go down to DN15. All the way through to a 2.5 meter line. Pipe has to be metallic. Certainly at the moment, we are working on getting the design to work on other pipe materials, but at the moment it has to be metallic. Temperature range, -40 to +400. That covers, I think, all your water industry applications. You can use it on liquids, steams, gases. We do look at gases a little bit more carefully. Actually, ignore that density one because most gases are below that, but that's just because we look at it a bit more carefully. The one thing you do need to look at a little bit carefully is your fluid viscosity. So your typical CHP 6% dry solids, well within that range, on CHP, sorry, well within that range, 6% dry solids. If you're in the thermal hydrolysis range, the THP range, which can be up to 20% dry solids, you'll probably find it sits outside that viscosity range. The reason why we're interested in the viscosity is because we do a calculation of the Reynolds number as part of our performance predictor. And that's just to check the flow conditions in the pipe, because what we want in the pipe is turbulent flow conditions. What we don't want is laminar flow, because if you're at laminar flow, the fluid in the middle bit of the pipe is hotter than the fluid at the wall of the pipe. But under turbulent conditions, you find that the fluid in the middle of the pipe is the same as the fluid temperature in the middle of the pipe is the same as the wall temperature at the edge of the pipe. So that's a typical calculation. That was one that was done on steam, 184 degrees steam, and it's comparing the process temperature to what a non-invasive design will give us, so you can get a rough calculation of what the error would be. That's an example on steam. Here's a live example from a couple of years ago. We did it on an aeration line effectively. So this is process air quality. So there's two non-invasives mounted and compared with a non-invasive and monitored over a period of time. And what we found is they just follow each other. It is just as good as a standard thermal well design. And you can see here the sort of temperature range was around about 30 degrees. It's actually sat at the bottom there, 27 degrees. The thing works fine. But what it did mean is they could you could hot fit or live fit the non-invasive, because you're not putting a hole in the line. You are just mounting it on the outside of the pipe. So no shutdown required to mount the non-invasive. We've got lots of examples of the non-invasive. So let's see if I can pull this screen up. Hopefully this works. So I've talked about this performance predictor. So hopefully you can all see this. If not, I can show it at the end. But the performance predictor is effectively, it's an online tool. It's available to yourselves. We don't have to do it. Generally, we do, because we take that burden, if you like. But here's an example I did for an aeration line, running it around about half a bar. I've put it in air, 8-inch line with a 6.4 mil wall thickness, running it around about 35 degrees. And you can see there the difference is 0.4 degrees C, which is comparable with a standard thermal well design. Sometimes people will say, well, what if my wall thickness is a bit thicker? Well, okay, I'll change that to 8 mil. And I can just scroll down. It's not so easy. And then we do a recalculation, a little bit thicker. It's made a tiny difference. Your wall thickness makes very, very little difference. We tend to have a feel for what works in an application and what doesn't. If we have any doubts, we'll do this performance check just to run it through. The other beauty of doing this is you can download it. So we can generate this, download it, send it to you. You can generate this yourself. So the link's at the top there, or it was at the top there. So you can do this yourself. So you've got ready access to the tool as well. There's nothing secret about it. It's just physics, effectively. So digital world, we're on to, I think, last slide pretty much. I've just put a very quick slide in on verification and calibration, because this is sometimes a question we get asked. So you can calibrate both pressure and temperature devices. So there's an example of a temperature device being calibrated in a bath and checked. For me, there is no substitute for calibration. Calibration is always a gold standard, but typically to calibrate a device, you need to take it off. So as soon as you take a temperature device out of the thermal well and you've taken it off to the lab to check it, how do you know your thermal well is okay? Your basic sensor can be perfect, but you don't know your thermal well. It's not the thing that's giving you a problem. And this is actually something we've picked up with the non-invasive. So some people now use the non-invasive design to go around and check some of their installed thermal wells. And if they see a big difference, they know there's a problem potentially with the thermal well. Where you can't take a device away to calibrate it. So some examples there earlier where there was no process isolation for a pressure transmitter, for example. This is where really verification comes into its own. So you might not want to go and calibrate your temperature device every 3 months, but you can go up and do a digital verification of the device. And what that effectively is talking to the device and saying, how are you working today? How are you working compared to the fingerprint when you originally manufactured? Are you still operating within specification? And from a device point of view, that will come back and go pass or fail. Or if it's a fail, it will typically tell you why I'm not happy. So at least you've got an indication of where maybe there is an issue. The only challenge of a verification, if you like, is it doesn't necessarily tell you if there's something going on in the process. But at least you know your device is working properly. And you can go, right, well, I know my instrument is fine. I've got a happy verification report. Let's now go and have a look at the actual installation, see if there's a problem with the installation. And that's actually quite a powerful tool. It's something I've used a lot, certainly on the flow meter side, which in previous life I had a lot of knowledge there. That's really, really powerful. And actually it's really useful in pressure and temperature as well, because you know your instrument health check is fine. My instrument is working as it was when it came out of the factory. You know to look somewhere else to see where the problem is. So that was very much a whistle-stop tour